Hey, hello, everybody. Hey, this is going to be the review for midterm review number one. In midterm review number one, we are going to have a block on a inclined plane, okay? And that angle is 32 degrees, and we have an initial height of 2 meters. So even though the block is initially written this way, we're essentially it's going to be at the top, and it's going to have an initial velocity. It's going to have an initial velocity of 0, okay? And we're going to calculate the gravitational potential energy. So even though this question kind of goes back to some of the stuff that we had way early on, we can see that it is going to be mixed. It's going to be mixed with stuff even that we just learned. So you guys may remember that gravitational potential energy from this last week is equal to mgh. Okay, so we're going to say number one is mgh, and our mass is 2 kilograms. So this is going to be 2 times 9.8 times a height of 2. So 2 times 9.8 is 19.6 times 2 is going to be 39.2. 39.2, and that is going to be joules. Okay, what is the initial gravitational acceleration down the ramp? And this is really, we need to go back to our free body diagrams. And when we draw a free body diagram, we're just going to kind of think of this block as being right here. So going down is the force of gravity. Going up is the normal force. And this, we're going to say that this direction is the x and this direction is the y. Remember, we want to choose a convenient xy coordinate system. So the x is going to be the direction it moves or potentially moves. And we can see right now that our vector mg is not moving in our xy coordinate system. So we're going to break this mg as the hypotenuse into these two components where that is a right angle. And if this is 32 degrees, then that's 32 degrees. And this one is going to be mg cosine 32, and this one is going to be mg sine 32. So remember, vectors can be picked up and put there. So this is the vector that's going down. So this is going to be 2 times 9.8 times the sine of 32 degrees, and 2 times 9.8 sine of 30 is going to be, this is our mass, okay? So when we do the sum of the forces is equal to ma, this is the force down the ramp, which is 2 times 9.8 times the sine of 32, but that's equal to 2a. And now those are going to cancel out. And our acceleration, is going to be, 2 times 9.8 sine 32 divided by 2 is 5.2, okay, or 5.19 meters per second squared, okay? So 2 is 5.19 meters per second squared down the ramp. Okay. What is the weight? What is the weight of the block? Now remember, weight is just equal to mg. So weight is equal to mass times gravity. That's going to be 2 times 9.8 and that is 19.6. Okay, so the weight is equal to 19.6, and that unit is going to be in newtons. Okay, what is the normal force? What is the normal force in this block? The normal force is we're going to take the sum of the forces in the y, and that's going to equal to 0. Remember, this block is not going to be moving up and down this way. It's not going to be levitating or sinking. So our force normal minus mg cosine 32 is equal to 0. Therefore, force normal is equal to mg cosine 32, 2 times 9.8 times the cosine of 32. 2 times 9.8 cosine 32 gives us 16.6. Okay, 16.6 newtons. 16.6 newtons is equal to the normal force. You guys may have noticed initially when you were looking on here that some of these answers were wrong, and by the time I finish now, I will change those in the document so they should all be right after this. So I apologize for anything that was ended up being wrong. Okay, now the length of the ramp, which is just this. This is really just a geometry question, okay? And we have the hypotenuse, which is what we're looking for, and we have the opposite side. We have the opposite side there. And so we're going to say the sine is equal to the opposite over the hypotenuse. So we want the hypotenuse, so we're going to say hypotenuse is equal to the opposite side divided by the sine of the angle. So in this case, that is going to be the opposite side is 2 divided by the sine of 32 degrees. And 2 divided by the sine of 32 gives us 3.77. And that would be 3.77. So 3.77 meters is the length of the ramp. Okay, question 6. How long would it take the block to slide down the ramp if it was frictionless? If it was frictionless. Okay, so now we have a lot of this information. Okay, now we're going to go back to our kinematic equations. Okay, and remember, as long as we have 3, we can figure out everything else. Okay, so we know that our initial velocity is 0. We know our acceleration down the ramp is 5.19 meters per second squared. And we know our distance down the ramp is 3.77 meters. Okay, so now we're looking for the time. Okay, and we need the equation, which would be the third equation from the kinematics, would be distance is equal to the initial velocity times time plus 1/2 at squared. So remember, the initial velocity is 0, so we got 3.77 is equal to 1/2 of 5.19 t squared. So we're going to multiply that by 2, and we are going to divide by 5.19, and then we're going to take the square root. So the 2 went up there, the 5.9 went up there. We're going to take the square root of that, and And we're going to end up with 1.2 meters per second. So our velocity at the bottom of the ramp, or sorry, the time is 1.2 seconds. 1.2 seconds. And that would be where's my calculator? Sorry. 1.21 seconds when we round. 1.21 seconds. All right. Question is 7. How fast is the block going halfway down if the ramp was frictionless? Okay. So if it's going halfway down, okay, then the distance is going to be half of 3.77. Okay. All right. So now we are looking for our final velocity, but this time our distance is going to be divided by 2. So 3.77 divided by 2, so that's 1.89. 1.89. And we can now say that V final squared is equal to V initial squared plus 2AD. We can solve for V final, and that's going to equal initial velocity 0, so we're going to have 2 times 5.19 times 1.89, and we take the square root of that, so times 2 times 5.19, and we're going to take the square root of that, and that's 4.42. 4.42 is equal to our final velocity. That's meters per second. Now remember, that's only halfway down, so velocity is equal to 4.42 meters per second. All right, and looking at question number 8. If the coefficient of friction is 0.25, what would the force of friction be? What would the force of friction be? All right, I'm going to get rid of this. Remember, force of friction is equal to mu force normal, and our mu is 0.25, and our normal force, remember our normal force was going to be, I don't think we figured that out. Okay, so we can see right here that the sum of the forces in the y was equal to 0. So we had force normal up minus mg cosine 32 going down. Therefore, we're going to have force normal is equal to mg cosine 32. So that's going to be 2 times 9.8 times the cosine of 32 degrees. And we are going to get 16.6. So 16.6 newtons. Remember, that's our normal force. And now that's going to go up here, 16.6. And we're going to take 1/4 of that, or times 0.25. And we're going to get 4.16. So our force of friction is 4.16 newtons. And that is going to be up the ramp, remember, because it's always going to oppose. It's always going to oppose the motion. All right. Number 9, how long would it take the block to reach the bottom if the coefficient of friction was 0.25? So now we're going to kind of combine. We're going to combine our two equations here. And now we're going to say the sum of the forces in the x is equal to ma. Now remember, down the ramp was mg sine 32. That was 5.19. And then we're also going to have minus, so that's down the ramp, that's positive. Minus is going to be mu force normal, which is right here, which is going to be 2 is the, that is going to be 0.25 times 16.6, and that this one we ended up having 2 times 9.8 times the sine of 32 minus 0.25 times 16.6. Let's check all that out here. So 2 times 9.8 times sine of 32 is 10.38 minus, remember, we got 4.16. That means it is 6.22. So our mass times acceleration was 6.23 actually, and that would be newtons. But now we want to divide by 2 kilograms, and that will give us our acceleration divided by 2 is equal to 3.11 meters per second squared. That is our acceleration. And I'm going to pause for 1 second. All right, sorry for the interruption. So where we were, essentially, when we have friction, it ended up having an acceleration of 3.11 down the ramp. Now remember, before it was like 5.19, so obviously the friction slowed it down. Now we're in a position to go back to the kinematic equations and to solve for the time it takes to reach the bottom. Okay, so again, we're going to have an acceleration that's 3.11. Our initial velocity is 0, and our distance is still 3.77. And we're looking for time, so we can say that distance is equal to VIT plus 1/2 AT squared. This is going to go away, so we're going to have 3.77 is equal to 1/2 of 3.11 times t squared. So 3.77 times 2 divided by 3.11. You could divide this 3.11 divided by 2 and get that 1.56 before or after. And then we're going to end up taking the square root of that whole thing, and that is going to give us the time. So we're going to have 3.77 times 2 divided by 3.11. That is 2.42. So take the square root of that, and we're going to have 1.56 seconds. So our time is equal to 1.56 seconds. All right, so keep plugging along here. How fast would the block be going when it reaches the bottom if the coefficient of friction was 0.52? All right, so I'm going to kind of erase this and get back to it, but it's that same information that we want to know. Okay, so we could do this in a couple of different ways. Okay, we could say V final squared is equal to V initial squared plus 2A D. this initial velocity. So we could say 2 times 3.11 times 3.77, and that is v final squared. So if we take the square root, okay, we can get that. So 2 times 3.11 times 3.77, and then take the square root of that, and we're at 4.8. 4.84 meters per second. Now we could also do another equation. V final is equal to V initial plus AT. This would be 0. Our acceleration is 3.11, and our time was 1.56 seconds. And 3.11 times 1.56 and gives us 4.85 meters per second. Now we can see that is essentially the same thing. It's just going to be a matter of the way we rounded. Okay, so either one of those is going to be fine. So we're going to say number 10 here. We're going to be going we'll call it 4.85 meters per second was our V final. All right, and now we have number 11. Okay, now number 11 is kind of pretty tricky. It says, at what maximum angle would the incline have to be so that there's no movement takes place? Well, that is going to be where the friction is balanced. The friction is balanced by the acceleration down the ramp. So I'm going to kind of redraw that right here. Now, as you know, we have talked about the difference between the coefficient of static friction and the coefficient of kinetic friction. And the static friction is almost always the same. For our purposes here, we're going to say this coefficient of friction is the same for both static and kinetic. It'll just make it a little bit easier. All right. So when we look at this, okay, this velocity down the ramp is going to be mg sine theta, mg sine theta. Now, remember, now we don't know what that angle is, so this is going to be this is essentially going to be an unknown for right now. And then up the ramp, remember, is going to be mu times the normal force, and the normal force was mg cosine theta. Okay, so this is down the ramp minus mu mg cosine theta, and that is equal to ma. But remember, we want to know where it's not moving. So this acceleration would be 0. Okay, and now we can solve here. So we can say mg sine theta is equal to mu mg cosine theta. And notice here that the mg's cancel each other out, okay? And we can divide both sides by the cosine theta. And now we have sine over cosine is tangent. So tangent theta is equal to mu. And we want to know what that maximum angle would be, okay, if our mu was 0.25, okay? So now we can say 0.25, and now we want to say the inverse tangent of 0.25, because remember, if we take the inverse tangent of tangent, it's going to go away. And so we can now just take the inverse tangent of 0.25, and that gives us 14. So 14 degrees. Theta is equal to 14 degrees. And that would be 14.0 degrees. All right, so let's put that over here in number 11, 14.0 degrees is our answer to that. Okay, now, how many significant digits should there be for each answer? Remember, the number of significant digits are based on the number that are in the original question, and each one of the significant digits in each of our values above is going to be 3. So our answer should be rounded to 3. Okay, so we should have three sig figs. Okay, all right. So our answer to 13 is, what are the units for force? And that is newtons. And the answer to number 14, what is the SI units for acceleration? Meters per second squared. And what is the minimum amount of work needed to move the block from the bottom to the top of the ramp if it was frictionless? Now, this really bounces forward. It bounces forward to the energy unit that we were kind of now on in week 8 and 9. But remember that in the beginning, we had 39.2 joules of potential energy. Now, if it were to go down here, the amount of energy that would convert, it would go from 39.2 joules of potential energy, and then that would change into kinetic energy. Okay. Well, if we were at the bottom here and we wanted to move it back up, we would have to apply 39.2 joules. And that would be the minimum amount because our velocity at the top would be 0. So there'd be no change in kinetic energy. So all of the energy would be used to making it go higher. So that answer really comes from the first answer, which is going to be our 39.2 joules. Okay. So the answer to 15 is 39.2 joules. And the answer to 16, what is the minimum amount of work needed to move the block from the bottom to the top of the ramp if the coefficient of friction is 0.25? Okay, so now we're going to still have this 39.2, right? But now we're going to add the work. We're going to add the work against the force of friction. So we have, remember, work is equal to force times distance, okay? So if this is the force of friction, this work is going to be the opposite of that, okay? And technically speaking, okay, the force of friction is negative, but we want the work to overcome that, so it's going to become positive. Okay, so remember that our force of friction is mu mg cosine theta, but now we're just going to multiply by that distance. Okay, we've already taken into account the cosine. The cosine would be 180, so that gives us the negative times the negative. We can think about it in different ways. So we're going to have 0.25, okay, times 2 times 9.8 times the cosine of 32 times 3.77, okay? And that is going to be 0.25 times 2 times 9.8 times the cosine of 32. Sorry, this calculator turned off. 0.25 times 2 times 9.8 times the cosine of 32 times 3.77 gives, what is going on? 0.25 times 2 times 9.8 times the cosine of 32 times 3.77. 15.67. 15.67 joules. Now, that is the amount of energy we need, okay, to overcome friction. Our 39.2 was the amount of joules needed to bring it up against gravity, and therefore we can just add this to 39.2, and we're going to get a total of 54.9. So plus our 39.2 is going to give us 54.9 joules, and that is equal to the amount of work to work moving it up against potential energy plus friction. And so number 16 was 54.9 joules. Okay, and 17 and 18 is what are the units for work, which is joules. What is the SI unit for energy? Joules. So both of these are going to be joules. Okay, that's it. And again, if you saw some wrong answers, and looking here, I don't know what happened, but there was a lot of wrong answers there. There will be fixed by the time you see this video to match all of these answers up there. Okay, we will see you in the next video on the review for midterm review number 2. All right, good luck, have fun.